So 1-5 angle relationships. So we have a few types of special angle pairs. That is adjacent angles, linear pair, vertical angles, and adjacent angles are going to be two angles that lie in the same plane, have a common vertex and a common side, but no common interior points. I'll come back and explain more about that. Should have it where you can only look at one at a time, but I don't, so you're going to write them all. You don't need probably all of these examples, or even you probably just need one. You may or may not need any non-examples for each of these. We'll just talk about them. Linear pair is a pair of adjacent angles with non-common sides that are opposite rays. And then vertical angles on the bottom there, that was the third part of our Wednesday activity. Non-adjacent angles formed by two intersecting lines. Yes. We just started. No, you'll need to wait a while. Adjacent should probably be a word that you've heard before, maybe not in this context. So I'm going to try to give you a visual of adjacent in general. So I'm going to say Mrs. Zimmerman. I know she's gone. I don't actually know the new teacher's name yet. Okay, so it doesn't really matter. I'm gonna just say, I'm just gonna call it Mrs. Zimmerman's room still. All right. So, um, my room and Mrs. Zimmerman's room are adjacent. All right. So it's the same word here, right? Why are they adjacent? They share a side, right? For the rooms, that's the wall. In the adjacent angles, that's one of their sides, right? And then they have a vertex in common, technically, right? That would be here where the doors are. And there is no way to be in my room and the other room at the same time, right? Then you would no longer have a side, right? There's a hole in the wall. So we would be able to take that up. It's not actually possible because there's like this extra ledge here. You'd have to be pretty tall to try to get your feet around into both rooms. But if you are standing in this room, you can't also stand in the other room, right? So that's all of these things here, right? Two angles that lie in the same plane. We're on the same floor, same level, right? Have a common vertex. That'd be like the point right between the doors. And a common side, that's the wall that we share, right? But there's no way to be in both rooms at the same time. So that's adjacent. Here, you have your vertex in common and your one common side, right? Same here, vertex in common and your common side. But you can't be inside of angle 1 or angle 2 at the same time, and angle 2. 3 and ABC are non-adjacent, so that'd be this angle here and the big angle. So they do have a common vertex. They do share a common side, right? But there is a way to be in angle 3 and ABC at the same time, making it non-adjacent. Right here. This angle is inside angle, or this point is inside angle 3, and it's inside angle ABC. All right, is that point inside of this angle? Yes. Is it inside of this angle? Yes. And so that is breaking that part of our definition, right? Similarly here, if we had angle 3 and ABC, they don't share a common vertex. They don't share any common interior points, but the problem here is them not sharing a vertex is the biggest part. They also, it would be a stretch to say that they share a common side, right? They do have a line in common, but that doesn't really mean their side is in common, right? Linear pair, you see the word what in here? Line, right? So it makes sense that it is a pair of angles on a line, right? So this one works, you have a line and an angle drawn in. The other one does not work because there's no line, right? Anyone have an idea of, this is kind of going back to Wednesday, what else is true about angles 1 and 2? They are something. So they're a linear pair, they're adjacent. This would have been in the activity we did on Wednesday. They are probably wouldn't have been in your notes, Grace, because it was in the activity. Starts with an S and is really long. Well, we'll get there on the next slide. All right. Does anyone remember what else was true about vertical angles from the activity? So again, vertical angles are like 1 and 2, and then 3 and 4 are also vertical angles. Do you know what's true about angles 1 and 2? The degrees are the same. Good. And 3 and 4, the degrees are the same. Similar to the question above, angles 1 and 3 would form a linear pair, right? And then there's going to be something that's special about them as well. So here that is. Maybe. Go. Angle pair relationships. Vertical angles are congruent, right? That is basically what Savannah was saying, right? Measures are equal, leads to them being congruent. Then we have complementary and supplementary. Complementary is two angles that sum to 90. Supplementary, two angles that sum to 180. And then what I was looking at for the last page, angles in a linear pair are supplementary. Notice that angles are complementary whether or not they are in a 90-degree angle, right? They just have to sum to 90. So it can look like the first example here where they're actually in the 90-degree angle, or angles 65 and 25 are complementary. Did I say supplementary? Complementary. Again, supplementary, same kind of thing. The statement on the bottom leads to an interesting true and false question, right? Or a sometimes, always, never. Supplementary angles form a linear pair. Is that true or false? Supplementary angles form a linear pair. Hopefully we're at least that far. All right, I'll probably say it throughout the year. Mathematicians are lazy. I'm lazy. Supplementary is too long of a word. I will almost always write it as SUPP. So supplementary angles. Angles is too long of a word. So you will also rarely see me write the word angles. More often than not, you're going to see me write the angle. As long as you know what your abbreviations are, you can and should do the same kinds of things, right? So with the amount of times that we'll write angles through the year, it probably seems maybe a little bit silly if we're just doing it 5 times, right? Just write out the word. But if we're going to write angles 50 or 100 times throughout the year, right? Having a shortened form for it will probably save you time, especially with writing, which usually takes a little longer anyway. All right, so what do you guys think? Is this true or false? Supplementary angles form a linear pair. Who thinks that's true? Who thinks it's false? All right, 0% participation does not work. You have 20 seconds to make a decision for yourself. If you don't raise your hand this time, I'm going to go back and just give you a 0 on the quiz from yesterday. So everyone needs to raise their hand. All right. Who believes that this statement is true? Supplementary angles form a linear pair. Who believes it is false? All right. Grace, you're the dissenting vote. Why do you think it's false? Okay. I think you're getting at it. So yeah. I don't know why this stopped working. That's weird. All right. What does a linear pair have to do? A linear pair must be two angles that are on a line and adjacent, right? Do supplementary angles have to be adjacent? No, right? So when we ask this question, right, for true and false, if it's not always true, it's false, right? So that's how mathematicians typically are going to look at true and false questions. It can be true, yes. It can be true most of the time or all of the time except for once. If there's one time where it's not true, the answer is false. So it doesn't matter how true, like how true it looks, right? If it's false once, it's always false. So supplementary angles form a linear pair. These angles are supplementary. They are not a linear pair, right? They're not a linear pair because they are not actually on a line and adjacent, right? Which is what a linear pair has to do. On the other hand, if it's a linear pair, it is always supplementary. So a linear pair is supplementary, is always true. That would be the opposite, right? So that would be always true. It's still not going to work for me. Line segments or rays that form right angles are perpendicular. Those two lines or segments are perpendicular. All right, I'm not saying we do this with every big word, but perpendicular is a pretty big word. I get tired of writing it. So more often than not, you're going to see me use a symbol for perpendicular. Does anyone know what that symbol looks like? Yeah. Maybe a plus. It's close. But that might get confused with an actual plus sign, right? So what was that? The two lines is going to be parallel, right, next to each other. So it's going to look a lot like an upside down capital T. So this is I already hate writing this word. All right, perpendicular. So if we called these line A and B or segments, well, I guess we'll move them into being lines. Lines A and B, we might write it as A is perpendicular to B. So again, that's how we would read it. A or line A even when I'm writing it out, I get lazy. So perp. Line A is perpendicular to line B is how we would write that, read that. It'd be describing this diagram. again, these are decisions partially that you need to make, right? You do need to know when you see this symbol that it means perpendicular. It doesn't necessarily mean that every time you see perpendicular, you have to use that symbol, right? If you can shorten it to PERP and you know that's going to be perpendicular, again, that's fine. But if you look at that and say, I'm not going to know what that means when I read through, if I read through my notes again, or if I'm using it for a quiz, then you probably just need to use the whole word. Nope. Don't write everything or necessarily anything. As we look at a diagram, there's things that we can assume about it. There are things that we can't assume. So we're going to go through some of those. Again, I don't think that you actually need to write down any of this unless there's one I might get to that's like, oh, this one's actually pretty important. So things that can be assumed, a lot of these you would assume that you could assume, right? It's really the ones that you can't assume that you may have assumed that you could assume that you can't assume. Sorry, that was supposed to be for fun, not. So these things actually can be assumed. I think that a lot of them you would think are already true, right? So all points shown are coplanar. So unless there's something in the diagram that would clearly show it to be non-coplanar, it is, right? Almost everything we do, with the exception of when we're talking about three-dimensional shapes, it naturally will be that they're in one plane, not multiple planes. G, H, and J are collinear. In other words, in general in a diagram, unless we have a reason to believe otherwise, if 3 points look like they are in a line, they are. Right? So it appears that J, H, and J are in a line. We can say that they are. Unless there's something that would clearly indicate that it's only 179 degrees and it looks like 180, right? But generally speaking, we're going to assume that a line, something that looks like a line, is a line. These points intersect at H. In other words, if it looks like they go to a point, the diagram can't do something where it's like you have a point here, oh, but actually the ray starts here. It's just so incredibly close that it looks like it's going together, right? No, if the diagram shows that it goes there, right? H is between G and J. So if the diagram says the point is between 2 points, it has to be, it can't have actually H over here somewhere. That generally, again, would be something you would just assume, but there's reasons for that being true that are important. This one kind of follows. L is in the interior of MHK. JHM and MHL are adjacent. Where are those? JHM and MHL. Again, if they appear to be adjacent, it follows from the ones above that now it has to be. Linear pair, that follows from being collinear. JHK and KHG being supplementary, that follows from them being collinear, right? So some of these are following from other parts. Things that we cannot assume. Things that we can't assume. We can't assume perpendicular lines. We can't assume congruent angles. And we can't assume congruent segments. In other words, with the exception of a line being a line, we don't assume angle measures at all. We don't assume lengths at all. So just because two things look like they're congruent does not mean they have to be congruent. How do we know in a diagram if things are perpendicular? There'll be a box telling us it's perpendicular, right? If that's not somewhere in the diagram, and then it's no longer an assumption, it's something we're told, right? That's basically it. Again, the things that we can't do mostly relate to not being able to assume something's measure or its length. Name an angle or a pair of angles that satisfies each condition. Two obtuse vertical angles. So we want angles that are obtuse and are vertical. So vertical being on opposite sides of each other, right? So I believe there are two. One of them would be that angle and this angle. So that would be angle GFH and EFC or EFB, right? The other you might use would be BCG and DCF. I don't need to erase that. I need to erase this. Linear pair with vertex at B. So we go to B. We go to B, right? And we need a linear pair. So we need to make a line through B. The only way we can do that is with A and G. So our linear pair would be angle GB, and you can use CF or H, and angle CBA. Right, so two angles on the same line together, and they are adjacent here. Name an angle not adjacent to, but complementary to FGC. This one takes a little bit more work. We have FGC. What is the measure of the angle complementary to FGC? The measure of the angle complementary to FGC. So FGC has a measure of, this is 90, right? This angle is 50, so this angle has to be 40. So a complementary angle is 50. So we're looking for a different 50-degree angle, right? Because it can't be adjacent to. So G, what was it? GBC. I don't think there's a way for us to know what the measure of that angle is. FED says it is 50, right? And so we could use that. Angle FED. In other words, again, what we're saying is that FGC and FED are complementary because one of them's 40, one of them's 50, that totals 90. Again, that's not to say that FGH is not complementary. However, it is adjacent, so it didn't fit the context that we had. Name an angle adjacent and supplementary to DCB. DCB. So adjacent means it has to share a side and a vertex. H what? What's the vertex of DCB? GC what? What? Did you say GCA? GC what? GCH. That would be the vertical angle. Those two angles are congruent, right? So we want the adjacent. So if it's adjacent and supplementary, a different way of saying that is a linear pair, right? So it needs to form a line on one of the sides. So we could do this, DCB and BCG. Or, right, we have BCD. We could also make our line this way and use FCD. Again, with FCD, you could also use HCD, but you only need one. Questions there? All right, let's look at two different sets of angles here. The first one, these two angles form a, yeah, they are supplementary. Again, because they form a linear pair, right? Two angles on a line. It's a pair of angles on a line. Since they're supplementary, that means they sum to 180. So we have x plus 20 plus x equals 180. X plus x is 2x. Two x equals 160. And x equals 80. In the lower diagram here, we have x plus 5 and x minus 5. These two angles are adjacent. They're two angles in a 90-degree angle, making them complementary, also meaning that they sum to 90. So that means x plus 5 plus x minus 5 is 90. You have a plus 5 and a minus 5, they just cancel out. So 2x is 90. When you divide both sides by 2, you get 45. Does this button work? Yes. Let's leave it with that. What kind of angles are these two angles? They are vertical angles. Vertical angles must be so it's two lines intersecting to form them, but the angle measures themselves must be equal, right? They are congruent. So that means that we can set them equal to each other because they are equal, right? The other way you can think about it, right? I'm going to do it on the other two angles, right? We can mark our diagram as congruent, right? We could do those with the two angles we have as well. So 3x equals 2x plus 30. Subtract 2x from both sides, and we find that x is 30. Don't plug those in because I made those numbers up and it does not fit the diagram very well. Well, you can plug them in. You get 90, right? That's clearly not a 90-degree angle, right? So bear with me sometimes as I do diagrams, they won't necessarily match up perfectly with what I have. Again, here they should have, they don't in the diagram. in general, the diagram is going to be honest enough about acute and obtuse angles. Do these two angles look like they sum to 180? No, right? So generally speaking, again, mine is wrong, but generally speaking, that means that they won't, right? So if you forget which one you're looking at least think about it and say, do I think that this is 180 degrees? Do these two angles form a line? And if your answer is no, you probably don't want to sum them to 180, right? Is there anything in this diagram that indicates they should sum to 90? No, right? It doesn't say they're complementary. There's no right angle. So again, don't think that. In the diagram, do they look like they're equal? Yes, right? So use stuff in the diagram that's visual. Again, there's things that we can't assume, but we can still probably use it to help us make judgments on things. Oh, that's yesterday's. It's 30 today, isn't it? All right. Questions there? Yes. Which one? The last one, the two angles are equal, so you set them equal. Two angles are complementary. That means they sum to 90. The measure of one angle is 21 more than twice the measure of the other angle. So one of the angles is x. The other one is 21 more than twice that. So 2x plus 21. And they sum to 90. So 3x plus 21 is 90. 3x is 69. And x is 23. What? No, 21 plus 69 is 90. Then we divide it by 3. This asks for the measure of the angles. So one of the angles is 23. The other one is twice that plus 21, which is 46, 67. 23 plus 67 is 90, and that's what they were supposed to be. Homework 8 to 16 even, 19 to 21, 36 to 41, and 49. Like 15 problems.